Hello, welcome back. Let's recap what we covered in the last video and then we'll go along in next few more action items for LSTMs. Last uh, uh, video we covered LSTM basics, which was the operations that are going on inside one particular cell of a LSTM model. So basically LSTM model is nothing but an unrolled version of this one cell, whereas every time step will have its own computations where the weights will be shared across the time steps, weights and biases, basically all the parameters, and input, the cell will take an input for that particular time step, hidden state from last time step, cell state from last time step, and it will generate hidden state and cell states from this particular time step. So there were four different gates and operations involved, which we saw um, in this code basically. So what was going on here is we initialized all those four set of weights. First set of weights for forget gate, where we'll transform x to forget gate output and h that is coming in here to forget gate output. Similarly for x transform to I and h transform to I. I is basically output of this particular gate, which will decide how much of this value will go through and add to the cell state. Then similarly for xg, which is the weight for the tanh before this tanh. Then xoho, which is for this yeah. So once we have all these, and this was the last set of weights and biases which would be used to generate the logits out of this hidden state, out of this hidden state, this weight and biases. Wherever we are transforming input into a gate output, we would have input embeddings as n embed and output as hidden dimension. For h, because previous cell h is also of the same dimension, so it would be hidden by hidden dimension. Then output would be, we are transforming h value hidden state to a logit, so it would be output of vocab size vector. Now we wrap them all into self.parameters, turn on the requires grad true. At the forward pass, we'll be unwrapping, we'll take x as input and b by t shape would be for x, batch dimension and time dimension. So we'll unwrap this into bt. We initialize our hidden states with zeros, which would be one hidden state for each element in the batch, and each hidden state will be of hidden dimension size. Same for sorry, it should be self dot. Same for C. Once we have initialized these, we'll get the embeddings using self dot embedding layer, which was here as we are transforming vocab size by n embed embedding table. Then we initialize a empty list for logits. We'll append the logits here for each time step. And for each time step, now we'll iterate from 0 till capital T minus 1. We get the embeddings indexed for that particular time step, because that would be the only thing going into the at this particular time step into LSTM cell. So we have to get a particular time step inputs, which would become b by n embed. So for each element in the batch, we'll get a vector of n embed size. Then we apply, uh, we multiply xt with weight for transforming x to f for get output. We multiply h, initial h, h from the last layer with whf and add the bias. So this operation is very similar in all of the gates before we apply any activation. So sigmoid, sigmoid, tanh and sigmoid. So these are the operations happening here. This first forget gate will decide how much of the information from this previous cell state we should forget. Second is this combination of operations here is deciding how much new information we should add to the cell state. Then using the updated cell state, we are taking 10H of this, and then we are deciding how much of that information from the cell state we should forget and or we should keep and make it as a new hidden state. And all the inputs to these gates are a combination of linear transformed combination of x and ht minus 1. So that's what is happening here. If you see, this updated cell state is a product of previous cell state and forget gate. So this is this operation, this multiplication, element wise multiplication, then it times gt. So this is adding of it times gt, which is happening here. Now h is computed as ot times tos dot nh of c. So this is the thing where we get ot, then 10h version of c, updated c is multiplied with ot and given as ht, new ht, or it is also used for logits. So once we have these operations, we basically get the yt for that particular time step, which is just linear transformation with self dot yh why, and add some bias to it. We append the yt as to logits. So logits will become a list of t elements, t tensors of b by vocab size. So at each time step we will have b by vocab size shape of logits. For each element in the patch we will get a vector of vocab size for logits. Once we have this list of t elements in logits, we'll stack them and return it to stack them along the dimension of 1, so that it will become b by t by vocab size, and will get it easier to calculate loss for backward propagation. So this is all the network looks like for a single layer of LSTM, and then we can as our usual method of training, we can do for maximum iterations, get batch, forward pass, value calculate loss, then zero the gradients, loss dot backward, printing some stats, update the weights. So this is our usual stuff. So now this thing is basically written with using only tos dot random initializations or tos dot zeros, and then torch cross entropy function is used for calculating loss. Some model dot grad functionalities, model dot data, etc. So it's kind of not utilizing PyTorch to the fullest, and therefore I noticed while training this method was not as efficient as if we could totally port this to everything being used from PyTorch modules like an dot module. You see the classes here are simple, written from scratch. They are not inheriting from an dot module. So if you do that, it would become much efficient to train the networks with GPUs, and we can iterate faster. Now I'll do that hands-on in this video, but for now let me go through this next step. So this is the blog post I introduced briefly in the last video on unreasonable effectiveness of recurrent neural networks. So my purpose for this video is to reproduce the results from this particular blog, where I'm skipping through the initial part where Karpathy talks about the recurrent neural networks and LSTMs. So we have to focus into this fun with RNNs part, where he writes a code to the LSTM. He trains it for different kind of data, text data, Paul Graham generator, where he concatenates all the essays of Paul Graham and uh, uh, trains LSTM to do the generations like the inputs, Paul Graham's essays. Then there's Shakespeare data to be trained with LSTM. Then there's Wikipedia data. There's some algebraic geometry, LaTeX data, Linux source code data, etc. So there are 4 or 5 kind of data. I couldn't get hold of with so much time all of these kind of data, but what I could is Paul Graham, Shakespeare, and a Python code data. So my Python code data wasn't very extensive and broad and of good uh, quality. I think it was very uh, basic. So we'll see at look at the generations and then understand what's going on. So I'll first. So basically, this is the code that I wrote uh, from scratch for multiple layer of LSTMs. Uh, I'll just show you. I'll just walk you through it so that um, it's easier to understand that it is more or less similar to what from scratch code we wrote for single layer LSTM. Here, this part, I wrote a text loader class, which is basically wrapping up all the data preparation we were doing without any classes earlier. So when you initialize this, we pass a text to it, vocab, s2i, train data, val data, these things to it. We memorize all of these. When we call from text method of it, it will you have to pass text. That's it. It will generate all these mappings and vocabs, etc. out of it, which we are doing explicitly in previous videos. So all these things are prepared, and then we return the class of with all these variables. So when we return the class, it will initialize, it will call the init and initialize all these attributes. Encode decode function, which is very similar to what we were doing earlier. Encode each character in the text and decode each token in the list of tokens. Get batch is basically we get random indexes equal to size of batch size, and then we um, index into the that split data and get block size length of tokens basically. So we have this, it's very similar. Then estimate loss was also very similar to what we have done in previous few videos. LSTM cell. So one thing to note here is now we are doing multiple layer of LSTMs. So this is one LSTM cell, how it looks like. This is multiple layer LSTM. So what it does here is we take vocab size and layers, input size, hidden size, and drop out as inputs. We initialize those, memorize those attributes. Then we define first layer, embed layer, emb layer, which is nn dot parameter of toss dot random. Now here again, I'm not using nn dot embedding, which would be a direct thing to do, but I'm using nn dot wrapping nn dot parameter into the same initialization as before. So you vocab size by input embedding size, which is an embed in our previous code. These are the factors I'm multiplying with to keep the activations at the initialization to be fairly diffused and close to zero. Initialize LSTM cells as a module list. Now we are going to append uh, layers to this module list. So for first layer, we have to append LSTM cell of input size by hidden size, because input going into X going into the first layer is of input size, which can be different from hidden size. And then second layer onwards, the input to each LSTM cell, second layer onwards, it would be hidden size by hidden size. So here we are wrapping, we are basically adding a list of LSTM cells for each layer. For if there are 3 layers, there would be 3 elements in this module list. Dropout is basically if you have any dropout yet, it will add to each of the layers if n of layers is greater than 1, and if dropouts it is greater than 0. Um, so these are the same parameters we define, we initialize for creating the logits out of hidden state. In the forward method, before we go to the forward function, let's look at what's happening in here, LSTM, one cell of LSTM, because we are appending to uh, so yeah, what's happening in this cell, which we are appending for different layers that we are configuring it for. So LSTM cell is basically initialization and forward method for one particular cell, which would represent one particular layer. Input size and hidden size would be the initialization inputs. So we'll be defining initializing three different parameters: WX gates, WH gates, B gates. So you see here this initialization for WX gate is something different. Input size is the input and output size is hidden dimension times 4. So this basically is times 4 because there are 4 different operations happening in the LSTM gate. If you remember, recall from our this code that we wrote for individual initializations, we were having these 4 set of weights and biases initialized. For this was for forget gate initialization, this was for candidate, potential candidate for cell state initialization or computation, input gate and the 10H operation cell candidate. Then this was for output gate initialization. So we are combining all of these 4 initialization together, where what happens is WXF, WXI, WXG, WXO, all of these are of same dimensions and embedded by hidden dimension. So we are concatenating them along columns. So WXHF, WXHF, and WXI, WXG, etc. So that's why we are getting to see here um, times 4. So this is being done basically for efficiency of matrix multiplications when we are doing all these linear transformations here, right? Xt times w self dot wxf, xt times matrix multiplied with wxi, wxg. So these are same operations happening with at 4 different times. If we concatenate all of these 4 weight matrices together, it would be just single 4 times larger matrix multiply. So that is basically more efficient to do in PyTorch as compared to 4 different matrix multiply of smaller sizes, I think. That's why we increase the size of it, and same for WH gates and same for B gates. So batch dimension, the biases will also be 4 times the original bias that goes into computation of single gate output. The different thing you'll see here is at the forward pass of one single cell, we'll have previous hidden state and cell state from previous cell. Using that, we'll just basically x will get matrix multiply with self dot wx gates. So this will be a large output you will get of n dimension by hidden dimension times 4, and embed by hidden dimension times 4. H previous will get the matrix multiplied with this wh gates. So here the outputs are you'll in the single long matrix you'll have output for each of 4 gates for both these things, x gates and h pref gates. Now gates output is you add these two and add the bias here also that we initialize to zeros. Now we chunk it we take 4 different chunks of the gates out and along the first dimension, along the column dimension. So you take 4 equal matrices chunked out of it and assign it to forget gate, input gate, cell state, cell candidate gate, and output gate, and then you apply activations to it and use them to calculate a further hidden state and cell state. So this forward method in LSTM cell would return hidden and cell state for one particular cell, and that would be used in a forward method here. So basically these LSTM cells that we are wrapping at, so for each layer one LSTM cell is basically a rolled version of for multiple time steps but rolled into one. So one cell is for one layer, and we saw that initialization is done more efficiently where we are not initializing four different weights for four different operations, but we are initializing one long weight matrix. So in forward method, what happens here is we have um, HS and CS, which is hidden. If it is none, both of these are none, we initialize them with zeros. So basically the first is initial start of the forward pass, we initialize them with 0. Then logits we initialize as blank list. We embed into X to get X embed layer from embed layer. Then for each time step we start basically a new HS and a new CS, which is basically a 0 like of HS. It is same as HS dimension, and it would be zeros, initializing it with zeros. Why we are doing so, we'll figure it out as we go along. So we take time step index into small t time step of X embed. We get the current layer. So HS you see is number of layers by B by hidden dimension, right? So for each layer we have B by hidden dimension size, hidden states. So for each layer, for when we are iterating on the layer, so for first layer we take the hidden state for first layer and cell state for first layer. We pass the cell state to LSTM cells, and we get because after embed layer the next thing is to go into LSTM cells. So we basically take the index into the first layer. We call it cell layer for the first one. So for cell layer we'll pass along our inputs and our tuple of hidden state and cell state of previous layer that we have calculated from here. And yeah, so we'll call the forward function on this. So in this particular layer of cell, we'll feed in the inputs, previous hidden and previous cell state. So we'll get new hidden and cell state for this from this layer, um, and so on. If we are using dropout, so this would apply dropout to new uh, hidden state, and then propagate it to the next layer basically. So we are doing this for each of the layers, iterating through the layers, and then once we have our final H new, which would be into this new HS. Uh, uh, so our hidden states and cell states finally are this, and we index into the last value of it, which is basically hidden state from last layer, to calculate our logits, which we are appending to logits variable. And then we stack all the logits along dimension 1 to make it as b by t by vocab size dimensional logits. So this will be a forward function for uh, for basically multi-layer LSTM. Now this is all not as optimized as we would want it to be, because we are still using the initialization in the format of toss.randn and wrapping it into an n dot parameter. It's very similar to what happens inside a nn.lstm kind of layer, but we are doing it manually. So training this was not as efficient as something if we would have done it using entirely PyTorch. Um, so let me show you some generations first. So basically what I did is, after I tested these working decently, I wrote everything in PyTorch, which is basically uh, this function where I use nn.embedding for embedding layer, nn.lstm here, which is directly a LSTM model from PyTorch. You feed in the input dimensions, hidden dimensions, number of layers, dropout, etc. And have a head layer at the last two calculator logits. You forward it to them, you get the logits. Then these logits and hidden states could be used to get the forward pass, backward pass, and optimization, etc. Using this model, I trained this model to uh, basically do the training for different kind of data, and which were, so we'll look at the generations. Shakespeare generation. So I trained a model for mm, where the hidden dimension was 1024 and input dimension was uh, I think also 1024 for two layers, and I got these generations out of that particular model, training it for until for early stop criteria. When the validation losses starts decreasing, it would stop. So these were the generations for Shakespeare text. You see, it's getting decent. It is not perfect. You still see something bad to pass your layer, which doesn't mean anything as such, I think, to me. But it is doing some good generation in terms that it is bringing in dialogues from the characters, small dialogue, some kind of monologues and small statements, etc. Lucentio, Trenio, etc. And I also checked that these characters are reoccurring multiple times, means it is following through its idea of maintaining the characters at least. So this was the generation I made. You can go to this link and go through it. So this was a pretty long generation I generated. And all these models I trained on a Kaggle notebook, which provides free GPUs, which is good enough to train for multiple hours, half an hour or so. So most of my models were able to train decently for within half an hour maximum. Then there's some Python generation. So this is the worst generations amongst all the trainings that I did, because my Python training data wasn't as good, which I got from somewhere in GitHub, which was a list of different Python problem solves. Basically, a lead code kind of problems were solved into it. So there were not much of variations present in that training data, but still I got some um, learnings done. It is defining functions, doing some documentation or comments. Basically, the indentations are happening properly. Here, den in it, it should be def. So there are a lot of mistakes are still here. But yeah, I think good enough training data should be able to give me a better generation of the code as well. But yeah, so this is the Python generation, and Paul Graham text from the essays that I learned is something like this. So it works. Anyone has to admit is the most powerful force over the long term, given an initial critical mass and enough time a programming language supports possible. Yeah, so this is a generation from Paul Graham training data. So as I showed you already, let me go to that lstm.py. So this was the class that I defined for LSTM, which is pretty simple when I use nn.lstm. So we don't have to do the internal manipulations of the tensors. Now explicitly here it is done with the LSTM, nn.lstm, and forward function also simplifies so much uh, that we can use the data directly. So for this I defined a text loader dataset kind of object, car dataset, using PyTorch's dataset class. It's more or less all similar uh, um, manipulation of the data to get the mappings, vocabs, um, train and val data, encode decode function, length function, and get item function, which would be used for getting the next batch when we want to train the data. This is the manual the text loader class that I wrote earlier, but for putting everything into PyTorch, I decided to go ahead with PyTorch's dataset class. And in the generate train and generate notebook here, you'll see that what I'm doing is reading the data from the file, defining some hyperparameters, batch size, block size, getting the base data set initialized, getting data set of train and val by calling the split function of it, then defining the data loader with all these parameters, which get me loader, train, loader, val, and then initializing the model with this device MPS. I was training on a MacBook, so I use the MPS device, which is faster than using it running it on CPU. But later I actually trained the models on GPU, on Kaggle free GPUs, so it was changed to CUDA. Initializing the optimizer. So here you will see small embedding dimension and hidden dimension, but while actually training it, I changed it to 1024 and 2 layers. For training, I took the maximum iteration of 20,000, but it never went that far. It was able to reach till maximum of 2,000 and it was stopped early. These are the hyperparameters for doing early stopping. Then you call get the next batch using loader train. You move them to the device that you want to train on. Model was also moved to the device. Then we call to get the logits, forward pass on the model, loss calculation, zero the gradients, backward step means basically taking a update to the parameters. Then all these are the uh, trickeries being done for doing the early stop, and we are printing some losses, etc. here. Also, for at each improvement in the model, each improvement in the validation loss, we are saving a model so that we have the best model saved at every iteration if the validation loss is seeing an improvement. Once we have this, we are able to generate with the model. We'll have to pass the mappings, etc. Mappings I2S S2I to get the generations. These are the few line of code if you want to load a saved model and then get your mappings, vocabs constructed out of it, read out of it, and then use these to basically initialize, load the state dictionary to the model, and then initialize optimizer from the model optimizer saved states, and then generate it. So this is what I use for generating all these texts generate part. But yeah, this is what training LSTM, generating from LSTM looks like. That's it for this video. I think I was able to generate these texts to a decent level as compared to this Andre Karpathy's blog, where let's say if Paul Graham generator, if you talk about, is not given generation here, but he told that there's one sample here. The surprised investors weren't going to raise money. I'm not the company with the time. There are all interesting quickly. So this is also not a very good generation, but yeah, we were able to do something similar to the lines of what this blog has done. Okay, so I think now we'll close our this part where we were talking about LSTMs and RNNs to do the train, and after this video I'll get back to working on the GPT-2 model, which the next step should be as our initial goal, and we'll then continue along building a GPT-2 kind of model, and further along more inventions in the language modeling LLMs, which will lead us to LLMs. Thank you.